Last September, Apple released the latest generation of AirPods Pro. Among the updates was something that was scientifically quite interesting: an in-ear optical sensor capable of measuring heart rate during exercise. Now, this was a big deal because it changes the form factor we're used to when it comes to wearable heart rate detection, which tends to be from either the wrist or finger if we're talking about PPG-based devices, or the chest if we're talking about ECG-based devices. The thing about AirPods and earbuds more generally is that they're already part of everyday life for a lot of people. They're used during runs, in the gym, and when people are commuting. And when a device that millions of people already wear begins reporting physiological data, it doesn't just become a piece of consumer technology. It basically becomes a wide-scale health measurement device. But there's one problem. Despite the scale of adoption, there was no independent evidence showing how accurate this new heart rate sensor actually is during exercise, particularly under dynamic conditions where heart rate changes quickly. And that was the motivation for our study. We recruited 40 healthy adults and brought them into our exercise physiology lab. Each participant completed a graded treadmill protocol that progressed from rest to walking to running and then recovery. Those transitions were a key consideration when we were designing the protocol. We wanted to avoid just evaluating steady-state exercise, so we included multiple intensity levels and rapid transitions, the kinds of changes that tend to challenge optical sensors. During the session, participants wore AirPods Pro 3 and a Polar H10 chest strap at the same time. The chest strap derives heart rate from the heart's electrical signal and is widely accepted as an accurate reference standard. We then synchronized the data between both devices and compared heart rate values in 5-second intervals. And the main finding was this: on average, the AirPods were accurate. The mean error was just over 2 beats per minute. There was essentially no systematic bias. The device did not consistently overestimate or underestimate heart rate. Across rest, light, moderate, and vigorous exercise, average accuracy was pretty stable. But while average error was small, the second-to-second differences between the devices became more variable at higher intensities. The limits of agreement were roughly plus or minus 10 beats per minute, which is quite high, and most of this variability occurred during those higher intensities of exercise. Physiologically, that makes sense. Optical heart rate sensing relies on detecting changes in blood flow using light. During harder exercise, movement increases, breathing becomes more forceful, the jaw and head move more, and the optical signal becomes more difficult to stabilize. So what we see is a pattern that is now pretty familiar across wearable technologies. Accurate on average, but less precise in individual moments, particularly when exercise becomes vigorous or highly dynamic. And that matters because accuracy is always relative to the intended use. For everyday fitness tracking, long-term monitoring, or understanding general training intensity, that average level of performance is fine. But for applications that require fine discrimination between adjacent training zones, detection of brief physiological spikes, or even clinical decision-making, a chest-worn or ECG-based system is probably the more appropriate tool to use. So the takeaway is not that AirPods were accurate or inaccurate, it's whether they are fit for purpose. Are you planning to use these earbuds specifically for exercise tracking, or is it just a useful add-on feature? Stepping back, that may be the most important point. Consumer technologies are evolving very quickly. New sensors are being released into products that people already use at enormous scale. But scientific validation almost always comes later. Now, our role as researchers isn't to slow that innovation down, it's to understand what these devices actually measure, how well they measure it, and where their limits lie. Because the future of digital health won't be built around specialized medical equipment alone. It will be built around everyday devices, watches, rings, and increasingly earbuds that people already wear. The question is no longer whether these technologies can collect physiological data. We already know they can. The question is whether we understand that data well enough to use it wisely.